Yeah, so I have started recording. Let us start the class. One second. Okay. Okay, where is this? Yeah. Okay, so today we are again, I mean, we are lagging by a class. So the some of the tricks of the trade that probably helps in better optimization, better learning, etc. Only we will scratch surface about those. These are basically the regularization and regularization strategies. Under that, many regularization strategies are there. So we will just scratch the surface, as I said. Oh, yes. And one of them is this parameter norm penalties. One of them is dropout. And apart from that, batch normalization that I think I have mentioned in the assignment also, that this we left out. So we will discuss about them. But again, very sort of scratching the surface. And the thing is that these things you will see, many of the things are actually not so much theoretically grounded. People have tried these things and empirically found to work more, well, so they have gone ahead with this. So that's why I will not spend so much time on it, but it is good to know all these things. And some of the things are actually coming from the machine learning literature also. I mean, it's not that it is very specific to deep learning. Some are, but some are not. So let me see. Yeah, it's working, but let me just change the color. Okay, how? Yeah. So so this is the agenda. As I said, introduce the concepts of regularization, dropout, batch normalization. How to? Okay. Anyway, so and the resources, of course, the book, mostly the book, chapter 7, as I said. I mean, as you know, that some of the times, most of the times here, if they are not very classical stuff, I take it from different papers, other online lectures. But as we take those resource, the source are given in the slides. I shall upload the slide after today's class. Okay, so let us first start with regularization. So regularization, again, this concept is actually coming from machine learning. So it's not too specific to deep learning, but again, since people have found that okay, deep learning can be very good with big data, etc. Lots of training data, etc. So they try to basically see that okay, if these regularization techniques, or in general the techniques that are particularly classical, if they can also be improved. So it's sort of a how can I say, mutually beneficial way that these two, many things have progressed. Not just that deep learning got improved, but classical concepts from machine learning, they also are needed to be tweaked to make them fit for deep learning. And in turn, you will see that that also has helped in classical machine learning literature also. Now, regularization is a concept that has been in use in machine learning, and it is concerned more about the performance on the test data than on the training data. So, of course, that is what we care for most, performance of the test data than the training data. You can have almost zero error in training data, but if it does not give you good, basically, performance on test data, then it is of not much use. So the generalization performance is what we care for most. And regularization is a technique that sort of enables the model to behave well. So behave well, what do we mean by behave well? It's so that it goes close to the actual minima and so on. Convergence is quicker. It does not take lots of time. It does not just swivel around the minima or some just get stuck in some local minima and may not say come out, all those things. But the idea or the end goal is that, okay, you have to do good on the test data. Now, there are these sort of high level definitions in the Goodfellow book, chapter 7. I'm just reading these. So many strategies used in machine learning are explicitly designed to reduce the test error, again, test error, possibly at the expense of increased training error. These strategies are collectively known as regularization. Again, it's a high level view. We will see some of the strategies. Also in the book, regularization is defined as any modification we make to learning algorithm that is intended to reduce its generalization error, but not the training error, or may not be necessarily the training error. So that is sort of the, again, high level definitions of regularization. There are many techniques of it. We will go one by one, a few of them. So these are some of the commonly taken techniques. One is adding restrictions on parameter values that we will see in the next slide. Adding constants that are designed to encode specific kinds of prior knowledge. So that is also one very useful trick. So, I mean, just to give you an intuitive idea, what this can mean is that suppose you are dealing with a regression problem and you want to basically find a function y is equal to fx, that is, you want to learn the function f, and suppose you know or your prior knowledge about the problem is that, okay, really y and x are actually very linearly related. Let's take the extreme case and we'll go above that. So in that case, what can be done is that, okay, you can probably, I mean, it might be that, okay, this is a very linear, not separable, since I have said regression, it's a linear fit, say, linear hypothesis function that you want to get, but you want to say, or you know that there are noises also here. So it may be that, okay, if you can say increase the degree of the polynomial a bit, that can also help to fit the data. So what you can try to do is that, okay, I will take a very large model, a very complex model with lots of, I mean, high degree of polynomial, but I shall say that, okay, most of them should be zero, the coefficients. So it will then try to learn a sort of a balance that, okay, that is the prior knowledge that is getting injected, that, okay, I know that the data is noisy. I know that the data is possibly coming from a less complex polynomial. Extreme case is linear. So let us try to basically give the flexibility to the model that, okay, it can handle complex data if the need be, but if not, it will just make all the kind of higher degree coefficients to zero. So this is sort of a trade-off that you can provide depending on your prior knowledge. So again, this is, I know this is a bit of hand wavy reason, but as you like sit down and think about it, this will start to make sense. One of the other use is ensemble methods, and a sort of sleek way to do it in a neural network is dropout. We will discuss about it in, say, 8-9 slides from here. Dataset augmentation. I mean, though some people hesitate to tell it as a regularization, but I mean, going by the definition that we discussed last slide, it's very well that is, I mean, the dataset augmentation may not, dataset augmentation is sort of trying to increase the variability of your training data, because you know that there are lots of parameters in deep learning model, so it will quickly overfit if you don't supply lots of data. But you may not have lots of supervised data at your hand because leveling is costly and so on and so forth. So what you can do is you can take one image, just slightly perturb it, slightly perturb the intensity value, slightly just say rotate it, flip it, many other things you can do, just basically to slightly perturb, so that at least you get a small variation about the original image. That way you can basically, you are injecting the diversity in the image. So that may not mean that in training data the training loss will reduce, or the training error will reduce, but it may actually help in reducing the test error. That is, the generalization will improve, because sort of the idea is that, okay, the model is now able to see more diversity, right? So this is I mean, going by the previous definition, I mean, the definition given in the previous slide, dataset augmentation is also included as a regularization. Now, this is, I think, one of the take-home message that you can take from this lecture, that in practical deep learning scenario, we almost do find that the best fitting model, which by best fitting model we mean in the sense of minimizing generalization error, is a large model that has been regularized appropriately. So you start with a large model, but you regularize it so that it has the requisite flexibility, but so that it can work well if the data is really, really complex. But if the need be, it can actually fall into simple models also, which works well. That's the thing. Okay. So again, this is a sort of high level overview. Let us go to a few of these techniques in a little more detail. One is this parameter norm penalties, which is this adding restrictions to parameter values. So the most traditional form of regularization to deep learning is adding penalties for high norm of parameters. So what this does is basically you try to draw, connect the dots of this and what I said about the prior knowledge, that is trying to fit a polynomial, a low degree polynomial, but take a high degree polynomial as your hypothesis. So this approach limits the capacity of the model by adding penalty, some function omega theta to the objective function, resulting in this. So objective function, we know that it is denoted by j theta. It can be for classification cross entropy, for regression, it can be the mean square error, and so on. But in addition, you add some function omega theta, which is just telling that the norm, maybe L2 norm, L1 norm, or any other norm, so say, depending on the application, you try to reduce. But if you think about norm is in a loosely said, it actually for a vector, it is parallel to the sort of a length of the vector, right? So then you are trying to basically reduce the length of the vector. That means you are trying to make their magnitudes small. That is each of the components of the vector, right? Each of the scalars. Otherwise, the norm may not be small. So if your learnable parameters, suppose for that same regression problem that I was saying, that polynomial fit, if you are actually collecting all your coefficients in a vector and you are saying that, okay, you try to, my objective will be to try to minimize this loss function. Along with that, the model should not have lots of high value of the coefficients. Okay, that is given by this, or that can be achieved by this omega theta. Setting omega theta is equal to, say, the norm, any norm, say L2 norm of the coefficient vector. So the approach limits the capacity of the model. Now, what do we mean by limiting the capacity of the model? That means you are basically, if you set these coefficients, higher degree coefficients to 0, you are basically telling that, okay, don't try to fit a very complex polynomial. Okay. So you are basically reducing the capacity of the model. That, okay, I mean, if there is really, really complex data, then it may not be able to model it. But that's what you want, that, okay, a trade-off. And this trade-off parameter or hyperparameter, so to say, is this alpha hyperparameter. So depending on the value of the alpha, how much importance this will get compared to this is basically decided. So this is a simple plot of this. So if, say, alpha is very small, suppose say 0, then it is actually this whole term, the second term is 0 or very small, and then j theta means the training error the training loss you are trying to reduce. So it can be that, okay, it's a very high capacity model, it is actually overfitting. So the training error is very less, but the test error is high. So the generalization performance is bad, because you are not allowing many of these coefficients, high degree coefficients, to grow. If, by not to grow, I mean that they are mostly zero, right? So it's as good as you are throwing a low capacity model towards this. Okay, now if you take alpha to be very high, then the training you are saying that your norm will be sorry, I think I said the opposite thing here. So basically you are in this left hand side, what you are doing is that you are allowing them to grow actually. So because alpha is 0, sorry, so alpha is 0, so it can actually fit every data. I mean, if that is the noise, I mean, it will try to fit every data. I mean, instead of a straight line, it might be this. So in that case, what will happen is that the training error will be very small, but the test error will be high. But if you give the alpha value very high, in that case, what happens? You are not allowing it to grow. So the coefficient for the high degree polynomials or high degree terms, higher degree terms. So that means that you are as good, it is as good as throwing a low capacity model. So the training error will be very high, test error will also be very high, because it can even be in extreme underfitting region. But as you can see that there is a very sweet spot that you need to find, and that comes from the experiments. You need to try with different alphas and see which works well. So this this term, this omega theta for neural networks and for L2 norm, if I just say that omega theta is not L2, I mean is L2, it is called a weight decay term. And why it is called weight decay, that will be clear in 1 or 2 slides. Now this is a very important thing. I mean, people sometimes just take this alpha value because alpha is sort of giving you the importance of this omega theta towards the total minimization problem, right? So how much importance I should give this to the second term. So people sometimes take, okay, whatever other people have taken in some other application, I'll take it. But some people actually experiment with that, and it is found that in many cases this has very important. I mean, this is of high importance. So the error, the test error is highly sensitive on this alpha value. So this weight decay parameter. I mean, one of the papers that is coming to the top of my mind is this fixed match paper, which came in like 2019, I think. It's from Google, I think, and it is one of the very sort of famous papers on contrastive learning, semi-supervised learning. They actually did a very good analysis of this alpha parameter. So with different alpha, what is the test error, training error, and so on. So they actually told that, I mean, just changing it slightly can even give you 10 points improvement, so 10% improvement, so and so on. So these are all empirically founded things. So I'll just I mean, I thought, let me give this side information to you. So one of the basically the variation I told is L2 norm, which is if thetas are the learnable parameters, then this is L2 norm. I mean, half is just for convenience, mathematical convenience. This is theta transpose theta, or the L1 norm. These are just 2 examples. I mean, you can have any norm. It is just the oh, I think it should be this. So there is a typo here. The absolute values sum. In neural networks, we typically choose the W's as the theta to regularize, not the biases. So what are the learnable parameters? Yeah, I see a raised hand with this. I'll just complete this and this slide, and I'll ask you to unmute. So we typically choose W's as the thetas to regularize, not the biases. So what are the learnable parameters in a neural network? It's all the weights and biases. But it has been empirically found that regularizing bias parameters can introduce significant amount of underfitting. So that way, you generally you add this parameter norm penalties for theta is equal to W's only, not B's. So for neural networks, this is sort of the regularized objective. This is the unregularized objective, and this whole thing J tilde is the regularized objective, and this is the regularization term. Okay. Okay, let me stop here, and Rishabh has a question. I'm asking you to unmute. Yeah.
Yeah, so I had a very basic question. I mean, what is inducing the error in the training data set? We know that the test data is, we can account of the test error because of the loss function, but what is it that is inducing error in the training data set?
What do you think? Just let me ask you. What do you mean by error in training data, first of all? If you just try to answer that, then I think you will get your answer. What is error in training data?
Yeah, so that is also a confusion for me.
Okay, so go back to the slides where I think it was before even the neural network I started. So the error, different types of errors that I have given it, right? But again, so the error is basically some sort of a difference that your prediction of the network that is given, and the training data, you have the labels, right? That you have the right decision. If it is a regression problem, what is the actual y for the x? And you have a y hat, that is the predicted value given by the model. So y hat minus y, it may be squared, it may be some other divergence metric, but some sort of a difference. Okay, that
So,
is.
but we optimize this loss function to minimize the test error. I mean, so I was confused about.
No, you are confusing. You minimize the training error. That is where the difference with optimization and machine learning, right? Please go back to the slides that I have. So optimization slides, please go back to that. It is clearly told, right?
Okay, sir. Okay, sir.
So what, I mean, if I come back to your original cause question, what is causing the training error? Then you see that if your data is non-linearly separable, or rather not linearly separable, and you are using a linear classifier, then of course there will be error. It is not separable. So there, all these things we have discussed about it. Okay.
Okay, sir. Thank you.
Okay, yeah, let me go ahead with this, and then I'll come back to Rishabh Tripathi. I see a raised hand, but let me try to go ahead with this. Okay, so L2 parameter norm regularization. So I have said that we call it weight decay also. So we can gain some basically insight into the behavior of weight decay regularization by studying the gradient of the regularized objective function. So I said this is the regularized objective function in the previous slide. This is unregularized, and this is the regularized term. Yes, regularization term. Okay. So this is for the L2 norm parameter norm regularization. As I said, the gradient, very simple, the gradient of this and the gradient of this. So the gradient of this we have seen from initial calculus primer, that this is basically half of, so yeah, it was half of W transpose W, so it is W. So the update step is this. So what is the update step? Previous weight times the step size and the gradient, right? Negative of the gradient. Okay. So if you do this algebraic manipulation, you will get this, right? This and this. Now, if you don't have this regularization term, that means alpha is 0. It will be just W minus epsilon grad WJW. This alpha term will become 0. So what effect is it incorporating or inducing this alpha? In addition, the addition of weight decay term modifies the learning rule to shrink the weight vector further before performing the usual gradient update. So usual gradient update means on the unregularized objective. This is what you would have gotten. But here you are saying that before even applying this term, you are reducing the W by epsilon times alpha times W. So that's why, I mean, they justify the term weight decay. So you are decaying the weight, and then you are basically applying this gradient. So that's where this weight decay term is coming. Anyway, let us go and do a little bit of analysis of this L2 parameter norm regularization. I shall not be very elaborative on this. Some of the maths I'll skip, but it is there in the book. So yeah, so further simplification of the analysis will be made by making a quadratic approximation to the unregularized objective function in the neighborhood of the optimum weights to the unregularized objective function. So what was the unregularized objective function? It was this JW, right? This is the you don't add any regularization. So this is the unregularized objective function, right? So what this analysis does is that, okay, you are approximating is by Taylor series the unregularized objective function itself, not the regularization term, yet it has not come. And suppose the optimum weight is W star, denoted by W star, and around that let us try to basically approximate the cost function as a quadratic cost function. Why quadratic? I mean, first of all, I mean, quadratic has a clear minima. It's a convex function. So that is one thing. And another thing is that, I mean, W star. So, I mean, if you are just approximating it around W star, which at least is the global minima. So just again, for the ease of mathematical convenience, we are doing. So now, what is the Taylor series form? It is, I mean, up to the second term is, of course, the first JW star, then there will be a term involving grad of JW. So basically grad of JW at, say, W is equal to W star. So I am just writing this equal to, or denote it as this, right? So star I was giving on the top. Okay. So, but at minima, this is equal to 0. So that's why W star being the minimizing value, this is 0. So the second term is not there. So the third term is, I'm just taking, I mean, and I'm ignoring the others. I mean, that we have seen earlier also for Taylor series, because this is around W star, which is a small value. So if you are multiplying them, small values, it will be ultimately very small, and you can ignore. I mean, you know all this from your first year calculus courses. So this is the term that involves the second derivative, or the Hessian. So what we have got in this slide, it is just the unregularized objective and a Taylor series approximation of this. Okay. Now let us go ahead and put this back in the regularized objective. What is the regularized objective? So that is the unregularized objective plus the regularization term. So this is the unregularized objective, but the Taylor series approximated one. I think I have denoted as J hat, this one, right? And this regularization term. So computing the gradient of this and equating it to 0, we get the minimizing W. So this is very simple. So if you do this and solve, I mean, take the gradient of this, equate it to 0, and solve it, the minimizing argument is this. Okay, so W tilde is H plus alpha inverse H W star. So the first thing that we can just very simply notice is that if alpha tends to 0, what do we mean, or what will we have if alpha tends to 0? If alpha tends to 0, then this regularization term is 0, right? So basically you are minimizing only the unregularized objective, only the cross entropy for classification, only the say mean square loss for regression. You are not trying to basically limit the unbounded growth of the norm of the parameter vectors. Basically you are minimizing, you are not using regularization. So you see that your minima is actually the true minima that we started with, that is W star. It is not different from the minima of the unregularized objective, and that makes sense because we are not using any regularization. Now, as alpha grows, what can be the effect? That can be seen using eigen decomposition of H. H is the Hessian matrix. Now, again, I will not go into detail, just give the sort of the result. I'm not going to derive or anything. Okay. So H is the Hessian matrix and it is positive definite. So you can do this eigen decomposition. This is this orthonormal matrices and this middle one is a diagonal matrix with all the eigen values. Q's columns are eigen vectors and so on, that we have discussed in eigen decomposition. Now, if you put this H value to the original solution of W tilde, that is the minimizing W, it will come like this. Now, what this means is that the effect of the weight decay is to rescale W star. So what do we mean by rescaling? That means what would have been the solution if we did not use regularization term, that solution will change a bit. And how does it change? It is defined by the eigenvectors of H, right? The eigenvectors of what? H. And H is what? It is the Hessian of Hessian means the second derivative of the unregularized loss, right? Unregularized objective. It does not involve the regularization term. But if again, this math is there in the book. I'm not going into there. Okay, before I go to the last line, just let me say what is W star and so on. So this is the W star, and basically this is the original objective function. So this is again the contour plot. This is the L2 norm penalty. This that comes as a circle. For L1 it comes sort of like a diamond and so on, right? So this is the L2 norm penalty we are discussing. And optimization theory tells you that, this is sort of a constraint optimization where you have the constraint, those Lagrange multipliers, etc. I'm not again going, but what is the essence is that the solution is this, where this touches, and there are this direction of normals, etc. But just forget about all these things. Just think that, okay, this is the solution. And the W tilde, again, I think this tilde has not been on the right place. And what it tells is that what is the difference between W star and W tilde. And it says that if the ith eigenvector of H is lambda I, that is in this, the elements are say lambda 1, lambda 2, lambda 3, that this is say the lambda 1 and this is a lambda 2. In that case, what we know from eigenvalue analysis is that this lambda is smaller. This lambda is smaller because it is the major axis sort of the ellipse. Again, I'm not going for that. You need to go back to eigen analysis and so on. But if this is smaller, then what happens is that the alpha has more role to play. So it will change a lot and so on. So again, I know this is probably I could have skipped this, but just to give you an idea and what is there in the book, just some analysis of it, I kept it there. But if you need to know more about it, just consult the book. That will be better. I think in book also you don't even get this eigen decomposition in too detail, but that is probably not required at this time. Okay, I will stop here for the questions. I see Rishabh has some hand raised. I am asking to unmute Rishabh Tripathi.
Sir, in slide number 6.
6, okay. Oh, okay. Yeah.
Sir, in this, can you explain this point number 3, sir?
Regularizing, yeah, this is an empirical finding that regularizing bias parameters can introduce significant amount of underfitting. Now tell me, what are thetas for a neural network, a deep neural network? What are thetas?
So
weights and biases, no?
Biases, yes, sir.
Biases. So if I am saying that it's a function of theta, regularization term, then you should think that, okay, omega for neural network will be a function of W and B both, right?
Yes, sir.
You need to minimize the norm of W's and also the norm of B's, right?
Yes.
They are saying, it has been found that empirically again, that it introduces error. What is the amount of underfitting? If you even ignore that, it introduces basically more test error. So basically, empirically, it has been found that you just don't regularize this.
Sir, by using this L2 or L1 norm, but I can see that whenever we apply this L2 norm to the bias term, it will like tends to 0, means our curve will always pass to the origin. Is it the case?
Yes, yeah, I mean, curve means if it is regression and it is straight line, that is definitely, but for yes, for any other higher polynomials also, yes.
Okay, so I was means, am I right or wrong? I was just want to confirm.
Yeah, that is true. I mean, for input 0, that will be 0, but what does that like, what does this have to do with this?
So I was thinking that I was relating this with the third term, so I didn't
No,
get
no.
the relation, so that's why I was.
Oh, no, I mean, I think that possibly does not have any relation to this. This is empirical finding again.
Okay.
Any other questions from anybody on this regularization? Because I think I am done with this norm penalty regularization. I'll come to this augmentation, etc. now. Okay, if not, then let us go ahead with the next thing. Yeah, these are simple. I mean, again, as I said, dataset augmentation. It is one way to get better generalization is to train on more data, because of course, I mean, you are having so much basically parameters that it can very easily overfit. So, but under most circumstances, data is limited. I mean, one of the very canonical example use cases medical imaging. So in medical imaging, you generally don't get access to much level data. Furthermore, labeling is extremely tedious task. So dataset augmentation provides a cheap and easy way to increase the amount of training data. So it is a cheap and easy way, as I said. I mean, I think I have discussed it when we were discussing the agenda probably. So color jitter, you are just changing the intensities of each of these pixels by a little value. You can do horizontal flip, you see. I mean, this is sort of placing a mirror on that and there, and you are just flipping it and so on. I mean, you can do vertical flip, you can do small amount of rotation, many things you can do. I think there was a paper that was given in the first presentation schedule, RAND-Augment. That is a very good paper, which just tries to see if you apply, I think out of 14 different types of these operations for augmentations, I mean, if you basically randomly choose them, say for 2, 3 in each of the mini batches, it works well and so on. So that paper is a very good empirical paper that you can look into. Now, another thing is this dropout. This is important, but it is, I think it has some relations with some of the techniques that you have already learned in machine learning. So one is this bagging. Okay, let me go ahead with this. So bagging is bootstrap aggregation, right? So bagging is a technique for reducing generalization error through combining several models. And this was given by Leo Breiman in 1994. So Leo Breiman was the sort of father figure for behind random forest. Okay, so the random forest classifiers. So what does bagging say? So bagging says that train k different models on k different subsets of training data. So you take generally the same size, so constructed to have the same number of examples. So the number of examples are same, that is all the subsets have the same number of examples, but the examples can be different and they are randomly chosen from the original dataset through random sampling, etc. And then what is the second step? Have all the models vote on the output for the text example. So you basically sample same size of, I mean, this is very much similar to this batch, mini batch ideas, right? So you have the same batch size. I mean, since this was pretty early, I mean, sort of first half of the 90s, I mean, maybe those terms have not come out, but in essence, it is doing this batching, right? Mini batching. So you take mini batch, you basically train different architectures. Now, what is different architecture? What do we mean by different architectures? So suppose this is a very simple base network. It has, say, in input 2 nodes, one hidden layer with 2 nodes and the output node, right? So if you train it on all the sort of nodes intact, this is this model. Now, if you say that, okay, I will not take this, that is whatever is the first component of the input, I'll just not take it. I'll just try to say classify or regress depending on the second dimension of the input. So then this is the network. Then, I mean, suppose what is this? This is, you are just omitting this node. Okay, that means, okay, I will just take one hidden, I mean, one node in the hidden layer, that will be it, not this. Okay, and so on. So you can basically, for the first mini batch, you can train this, for the second mini batch, you can train this, for the third mini batch, you can train this, and so on, right? So that way, you are, what are you basically trying to achieve? You are actually telling that, okay, I am relying on different hypotheses. So one hypothesis is that I will have two nodes, I mean, one hidden layer, and in that hidden layer, two nodes, and I will have two components of the input, and so on. That is the first one. Then the next hypothesis is, okay, I don't know if it may be that the first component of the input may not be important. So let us drop that and try to go ahead with the hypothesis. Maybe another one is that, okay, in the hidden layer, the only hidden layer, I will not take two nodes, but one node, and that is the left node, and so on, right? So this way, you get different ensemble of networks. We have sort of discussed about ensembles, and we have seen that ensemble of architectures give you sort of 2% improvement sometimes. AlexNet used that, VGGNet used that, I think GoogleNet also used, and so on. So, but there was a slight difference. There, the ensemble is all the, I mean, all the components, or like all the members of the ensemble is this same base network, but they just basically start with different initialization. So the initialization of those Ws are different, but they are not sort of removing the neural networks. Again, I have told it just so that you understand, but they are also applying this removal, which is called dropout, where I'm going to reach. But a simple ensemble can be such that, okay, you take one network, you don't even remove the nodes, just basically give different random initialization, and that will give you different members of the ensemble. That also you can do. So now the basic idea is that you can try to drop some of the nodes, okay, and that will give you different member of the ensemble. Now, what will you do during the test? That I will come. But dropout is a computationally inexpensive but powerful extension of bagging. So how does it do? Training with dropout consists of training subnetworks that can be formed by removing non-output units from an underlying base network. So basically, you don't remove this. Other than that, you basically randomly drop some of the nodes, and you try to train with one mini batch, and so on. So that way, it is again following the bagging idea, but it is computationally inexpensive. You don't have to change it by yourself, maybe for one mini batch, and so on. Okay. Now, and again, another way of computational expense or reduction of computational expense comes to the testing phase, that I will come. It's an approximation, but it gives pretty much good result. Now, this is another intuition behind why people think that this thing works, dropout. Suppose you are trying to say, suppose another way to view this dropout is to see it as preventing, say, two biased features. So suppose you have a neural network that learns to identify a cat, right? Say there is a neuron which really fires whenever, say, it sees a ear, or another neuron which, say, fires if it sees farts. Okay. So basically, if you concentrate on this neuron which has learned to, say, recognize a ear, it can basically fire on other, or it can, it may say, associate cat with ears. I mean, if just this neuron is always very strong compared to the others, but there are other cat-like features, right? So what dropout enables is that the network does not become too dependent on such few traits. Maybe that I mean, your data set actually has all the training images of cats has ears. So it might be thinking that, okay, ear is a trait which will definitely classify cat. Okay, so, but that may be wrong. There are other cat-like features, and there may be other examples, other animals which also has ear. So this gives, so what, I mean, this dropout enables this, that the network does not become too dependent on such few traits. By dropping such neurons off, that means these neurons say, and training the network. Suppose if I drop this network for some images, it forces the network to pick up on other traits of the cat. For a cat, for example, this tail, or has claws, etc. So some of these neurons may slowly start to pick up that cats also have tails, or it also has claws, and so on. So the network will be more robust at it can identify a cat by even if the ear is not captured in the cat image. So in the test image, maybe the cat is not there. Sorry, ear is not there. Still, it will be enable. It will enable it to identify it as a cat. On the other hand, any animal with ear then will not be classified as a cat. So this is sort of the intuition that people give. Why it works, or I mean, but this is also true for bagging as well. It's not just dropout. So dropout at test time. Now this has some complications, but I have tried to summarize it. So what will you do when you do the inference or test time? So ideally the randomness would have to be integrated out. What does that mean? That, okay, what do you do, say, for suppose the Monte Carlo approximation, or simple trying to estimate the probability of head of a coin, right? So you toss it a few times, and then lots of times, and then basically the proportion of heads out of the total number of tosses, that gives you an estimate. But it's ultimately an estimate, and that actually, again, I'm not going into the detail, but comes from this Monte Carlo approximation theory. So if you have not heard this term, that's fine. But if you have many things, many networks, and you need to come up for one image, one decision, what will you do? You will pass the image through these many networks, and you can do many other, I mean, sort of, you can take many strategies. One is that, okay, I'll average the prediction. That will be it. I can take the max, I can take the majority vote. Say if majority of it is telling that it is cat, I will take it. So some sort of a approximation you do. Now what the dropout, guys, I mean, this is a paper from Geofinton's group, and I mean, if you go into this slide, Karpathy's slide, you will see that there is anecdote there. I mean, they were not, I mean, this idea was very sleek. It is based on bagging and so on, but it was not working really good. So they had to do a little bit of math, and that math's approximation is this. Basically, the same thing, that you have to take an expectation. So this empirical average is a approximation of the true expectation. So if they do it and just assume everything is linear, then they come up with this rule. But again, it is not very exact. That's why it is saying approximation to this approximation. The first approximation is Monte Carlo approximation, and the second approximation is this thing, that, okay, we are assuming linear. So can this be done in a single forward pass that they are assuming? And if you can do it in a single forward pass, it is computationally inexpensive, right? So what is the single forward pass doing? Telling that you don't need to pass it through different subnetworks by randomly choosing different neurons. Okay, you just pass it through the whole network once, that image. Can this be done without dropping any neuron during the forward pass at test time? So that's what I said, just the last sentence, that through the whole network. So how do you get the effect? Get the output of the network at test time with all neurons on, So all neurons on, keep the all neurons on. I mean, or by on and off, I mean, you are dropping, then we say that it is off, but keep it on. Scale down this by multiplying it with the probability value with which neurons are dropped during training. So suppose you said that, okay, with probability P can be any value between 0 and 1. Suppose it is say 0.2. So then with probability 0.2, during training, this neuron will be dropped. With probability 0.2, this neuron will be dropped, and so on. So in one mini batch, maybe that this neuron gets dropped and this neuron does not get. So this p value you need to take care of, or like store the p value, just the hyperparameter. And whatever you are getting in the test time by passing the image through it, by keeping all of them on, you multiply that ultimately with that probability value to get the prediction. Again, the maths I'm not going, I think the book does not also have it, but it is said that it is assumed linear everything. Second way is basically just the inverse, a tweak of it. During training, compute the output of the network that you get after dropping out neurons with probability P. During training itself, scale up this by multiplying it with 1 by P. At test time, get the output as what is coming by keeping all the neurons on. So during training, you basically multiply with 1 by P, and then at test time, you don't have to multiply with anything. Here it is saying that during training, you don't do anything. So you get during testing by multiplying with P. Okay, so I think I have 3 more slides to go. Oh, okay, I think 4, but yeah, this is the last slide for dropout. This is a fun intuition. I think, when did it came? I think probably in 2017 or something, this tweet came. I think I gave it, took it from tweet. Srivastava. I mean, this is in another paper, but yeah, this is the paper where dropout was introduced. Dropout, simply described, is the concept that if you can learn how to do a task repeatedly whilst drunk, you should be able to do the task even better when sober. So you can think about it that, okay, I mean, I am just like imputing some of the nodes of the network, and I am saying that, okay, you can, I mean, do well. I'm just asking you, you have to do well. If you can do well there, then you are certainly going to do well in your, when you are basically, you have all the armories on. Okay, now let us stop for today. I think even if I start, I shall not be able to complete these 3 slides on batch normalization. But I shall basically at least start this. The last slide, because it is important. Let me do it. Okay, it is one thing again coming from, I shall wait for the question after it is done. So batch normalization is coming from again machine learning. So in logistic regression, you must have seen that if you do the normalization, that is, you subtract the mean of the features and then divide it by the standard deviation, it makes the basically optimization very efficient. That is, it so how I mean, it makes this well behaved, these losses. So it is not these elongated ones you have seen in I think optimization discussion, that if you have these elongated sort of contours, they are very jittery. So you can basically get away with this by making them normalized. So it has 0 mean, it will ultimately have 0 mean and the features and standard deviation 1, and that actually does wonder. So it speeds up the training. Speeds up the training means it does not jitter, okay, with I mean the optimization. Now how about a multi-layer neural network? Because this is logistic regression, just one input and then one p-activation, activation, and that the last, I mean, that activation is the output. Now what happens to multi-layer neural? Because you have a lot of input, I mean, not lot of input, lots of pre-activation, activation, again pre-activation, activation, and so on. So what do? You just normalize this. That will not work good. What you do is very simple extension of this, that you basically normalize this activation function. So you can take that this as the input to this. So you just normalize that. But it has been found that generally normalizing not the age, that is what you get after applying activation function, but if you normalize using pre-activation, that will that generally works better. So I will go ahead with this, or I mean stop here. And I mean, this will give you the idea of the batch normalization that you just require for the assignment. It is just one line of a code, and the 2 slides I will complete basically again next class. Now there is one thing that I need to basically